Next up, without further ado, we have Dave and Pranav from Facebook.
Thanks, Jeremy. Let's imagine that you're creating an app. You want to pick a language that allows you to iterate quickly. How about Python? And a framework that prevents you from having to reinvent the wheel. Something like Django. You hire a few engineers, and while they're busy working on features, you focus on making deploys as fast and seamless as possible. And it works. Your app is being deployed 30 to 50 times a day. Your engineers create a ton of new features that your users love. The app is highly personalized, so each new user that joins means more requests hitting your backend. People really like using your app, so they tell their friends. And their friends tell their friends, and so on, until all of a sudden you have explosive user growth. You can still move fast with Python, but it isn't the most performant language in the world, and that's starting to show. And your frequent deploys, they're now an opportunity to release inefficient code multiple times a day. Sounds like you've got a scaling problem on your hands. If you're not careful, your infrastructure demand can grow faster than your ability to keep up, and that can cause serious reliability issues and prevent you from shipping features. What kind of tools would you build to help your backend scale to over 1 billion users? Hi, I'm Dave.
And I'm Pranav.
We're going to be talking to you today about some performance monitoring tools that we've built to help Instagram scale and how they've evolved over time.
To support more users and more features, you need more machines. While dealing with explosive growth, it's very important to be able to quantify your infrastructure demand and be able to forecast it for the near future. Let's take a look at how we modeled the demand growth problem at Instagram. Infrastructure demand can be measured as a simple product of the number of active users on your app and the number of resources you need to support a single user. How would we want to move these metrics? Lower infrastructure demand translates directly into lower CapEx. So naturally, we want to keep this as low as possible, or at least prevent it from regressing. User growth is a key company metric, and we obviously want as many users to use our app as possible. Therefore, infra demand growth typically matches or exceeds user growth. This leaves us with the resources per user metric. To help the app scale, we want to minimize the number of computational resources spent on a single user. Infra optimizations can provide one-time wins, but do little to stem the steady flow of regressions that are inherent to this metric. New computationally expensive features are launched all the time, and in the process, we often end up pushing inefficient code to production. If the resources per user metric is not kept in check, the number of resources you need, the number of servers you need grows way faster than the number of users you support. This obviously affects the scalability of your app. The formula is still fairly abstract. What resource should we measure here? We could measure machines. However, machine specs change every year, so the metric won't be useful for long-term tracking. Since our server workload is CPU bound, we use CPU instructions as a proxy for machines count. We chose instructions because when you measure the cost of requests in cycles, it tends to vary with load. To detect and fix CPU regressions, we started an efficiency program. The program is a cross-functional collaboration between performance engineers and product teams. But if such a program is to succeed, it needs to be data-driven. Product teams need to be able to accurately estimate the computational cost of their features. This helps them plan and prioritize features better. And performance engineers need to be able to detect small regressions and attribute them to code changes or new features. We quickly realized that granular perf data is the key to success here. We found 3 levels of granularity were sufficient to empower product teams and perf engineers alike: the endpoint level, the function level, and the stack level. Endpoint level metrics are useful in tracking the long-term efficiency of features. Function level metrics are useful in detecting regressions caused by code changes or features. And stack traces are useful in generating visualizations to debug or triage regressions. Now that we've gone over why efficiency is important and what data is needed for a successful efficiency program, let's take a look at some of the early profilers that we built. Since we deploy code very frequently, perf analysis is complicated. We can't perf test every commit before we push it to production, and feature flags can make regressions appear at any time. A bulk of the regressions can only be seen in time series obtained from production data. And to make sure that the data is statistically significant, we need to be collecting it from most of our hosts, or almost all our hosts. Our initial strategy was to instrument the Django application to collect perf data for a subset of requests and log them to Scuba. Scuba is an internal tool we use at Facebook to store aggregate, and visualize data. Collecting endpoint granularity data is easy. We created a new middleware in Django that would read hardware instruction counters before and after every view function was executed, and the delta would be logged to Scuba. The simple endpoint profiler allowed us to track the infrastructure demand of an endpoint over time. By combining the endpoints that support a feature, we could suddenly track the infrastructure demand of a feature too, which is a really neat feature for product teams to have. For function-level profiling, we started off with cProfile, the standard Python profiler that ships with Python. The concept is the same. We enable the profiler in middleware before the view function, and we disable it after the view function is executed. The stat dump is processed and then sent to Scuba. cProfile provides us with function-level metrics annotated with stack traces. The function-level metrics are fed into QSUM-based regression detection algorithms, and the stack traces are used to generate call graph visualizations like the one shown here.
So Pranav, you've instrumented your code and you're producing some data. I'm curious, was the data initially good enough to allow you to do good regression detection, or were there some issues that you ran into?
I'll be honest with you, Dave, the data wasn't great. This is a time series showing the cost of a function that was modified twice in succession. We expect to see 2 jumps here, but the data is so noisy, we have like 20% noise, that it's hard to make out jumps or do anything useful with the data. Our workload also had strong seasonality, which can be very difficult to remove from a noisy time series like this. As a result of these problems, our detection workflows suffered from very high false negative and false positive rates. Not a great thing to have. But why was the data noisy? The answer partly lies in cProfile's methodology and also partly in our sampling methodology. cProfile works by registering a callback that the CPython runtime executes before and after every function call. This obviously is very, very expensive, so we need to maintain a very low sampling rate to avoid taking a hit on perf. And sampling infrequently on requests produces large amounts of data in very short bursts, which adds to the noise that you saw before.
So I know that asynchronous frameworks are really popular these days, especially in Python. Were you able to get good stack traces for things like async.io?
We use async.io at Instagram, and this did affect our ability to get complete stack traces. Let me explain. So Python has a global interpreter lock, which makes it difficult to parallelize I/O operations in a performant way. So like many other companies out there, we use async.io at Instagram. A consequence we have to deal with, however, is broken stack traces. Consider the call tree on the left. We have a coroutine A that gathers 3 coroutines B, C, and D. When you look at the perf data, you expect to see a flame chart like the one shown on the right. We have A show above the event loop, or the async.io loop, and we have coroutines B, C, and D show up above A. But this was not what we got with cProfile. We ended up seeing a flame chart that looks like this. You can see that the links between B, C, and D and A are lost, and B, C, and D show up at the same level as A. This makes A look cheaper in terms of inclusive cost, and the broken links make it difficult to debug regressions. Getting full stack traces with async.io required us to patch a lot of the async.io implementation. We could no longer use cProfile. We had to develop our own callback to pass into the Python runtime. The callback had to do the instrumentation required to collect perf data in addition to doing the bookkeeping required to get async stack traces. The new async.io aware profiler had a higher overhead than cProfile, so we had to lower the sampling rate further. And this obviously made the data quality even worse.
So often folks call into native code from Python for interop and performance reasons. Were you able to get full stack traces into things like C extensions?
This was probably the biggest problem for us. Python isn't a very performant language, as all of you guys know. So we often rewrite hard code paths in native C, C++ code. And we use a language like Cython or C extensions to bridge the gap between Python and C++. While this has some nice perf benefits, we lost complete visibility into the native code segments. Consider the scenario shown here. We have a Python function A that calls into some native code. Since we instrument only the Python code, we're able to profile just A, the function A, and the top of the native stack, which is function B. We lose visibility for everything below. To make things worse, we often have C++ threads running on the same process, and we have 0 visibility there. To summarize, our instrumentation profilers had some serious limitations. The data quality was awful, stack traces were broken or incomplete, and we had 0 visibility into other threads on the same process and other processes on the same system. There were some positives, however. These profilers were easy to debug, easy to maintain, easy to build. And we were able to inject all sorts of application-specific metadata into the perf data. We're also able to get function call counts, which can come in handy in debugging some regressions. The pain points, however, grew larger over time. As more and more code was converted into C or C++ libraries, our coverage dropped. To keep up with our growth, we had to catch more regressions with higher confidence. We couldn't have too many alerts firing onto our on-calls. So we had multiple efforts to improve these profilers. We tried calibration to remove overhead, to remove bias, and we also tried removing the overhead of C profile. But the problems persisted. Eventually, we reached a stage where we realized that instrumentation was simply not viable for us.
So we decided to try a new approach to solve these issues and created a system called PyPerf. If you're familiar with the perf tool for Linux, you can think of PyPerf as sort of our souped-up perf for Python and Instagram infra. PyPerf is a sampling profiler that doesn't rely on instrumenting Python code. It runs as a standalone process and lives on all hosts that Django is running on. Our goal was basically to get the same stack and function level data we were getting with the instrumentation-based approach before, but we also wanted to provide a consistent view into both C and Python stacks while minimizing the overhead of profiling. So when you run perf, it grabs the C stack on a regular basis, let's say every 5 billion CPU cycles. It then symbolicates the stacks it grabs, meaning it turns raw numbers into function names, line numbers, etc., as shown to your left. PyPerf does the same thing, but it also grabs the Python stack and symbols. But we're no longer running in the process where the Python interpreter is running. So how do we get its stack? And how do we turn that stack into something meaningful? To do this, PyPerf uses a kernel feature called BPF. Before we continue to dive deeper into PyPerf, we need to take a minor detour to talk about BPF. BPF is a virtual machine that runs programs which are submitted to the kernel from user space. You can hook up BPF programs to various triggering events that occur in the kernel. For example, packets arriving, context switches, or in our case, perf events. Now, submitting arbitrary programs to run in the kernel sounds like a recipe for disaster, but BPF prevents us from being able to do dangerous things by limiting how arbitrary these programs can be. Specifically, BPF programs have the following limitations. They can't loop. There's a hard limit to the number of instructions that a single BPF program can contain. There's a very limited stack size, 512 bytes, and the API is quite locked down. Even though you're running a program in the kernel, it's running in a virtual machine. You can't just call printk or kmalloc. You have to use the functions and data structures that the BPF runtime makes available. The combination of these things makes it very hard to shoot yourself in the foot. For our use case, BPF provides the functions we need. Specifically, we can grab the system stack, we can dig around in the memory of another process, and we can grab some other metadata as well. It also provides a few data structures which we use to communicate between user space and kernel space, like a generic map structure and a perf buffer. Let's walk through a typical PyPerf run. First, PyPerf digs into the binary of the running Django process to grab the addresses of some internal Python symbols. It uses these addresses, plus some struct offsets that it calculates from headers it links in, to determine where in the address space of Django it needs to grab the stack. PyPerf then generates a tracing program in C, which is compiled down to BPF bytecode and loaded into the kernel. The Performance Monitoring Unit, or PMU, is a chip that lives on Intel processors that provides useful features for folks writing system performance monitoring programs, which we very much are. In our case, we configure it to wake up the BPF program every certain number of cycles or instructions or LLC misses. So every time the configured number of, let's say, cycles occur, the PMU says, hey, BPF program, wake up and do whatever you were written to do. What our program was written to do was to take the system stack and then dig around in the Django process to grab the Python stack and symbol table. The system stack, Python stack, and Python symbols are passed back to the PyPerf user space program via a perf buffer and, in the case of the symbol table, a BPF map. We symbolize both of these stacks, annotate them with various types of metadata, and send them off to Scuba. So we've grabbed these two stacks and we've symbolicated them. What can we do with this data? Let's look at a system stack first. Here's a contrived example of what a system stack might look like. Notice that there are some function calls like py-eval-frame default and py-call-object. This is the interpreter telling us that it's evaluating some stack frames and manipulating some objects. But we sort of already knew that the interpreter would be doing that. That's kind of the entire job of the Python interpreter. We care about which stack frames it's calling into and which functions it's manipulating. The Python stack we grabbed has this information. In this case, it looks like we're doing the very important job in Python of parsing JSON. We use some heuristics to combine the two stacks. The result is a merged stack that looks like this one, where what's happening in C land makes sense, as well as what's happening in Python land.
The mixed stack sounds amazing, but what about async I/O? Do you think PyPerf can get full async stack traces without actually modifying the Python process itself?
So we were able to do that, but it was quite challenging. Since our tracing code is in BPF, we need information about who created the async task to be in memory somewhere that we can find. As a reminder, since we're in a separate process, we can't call functions in the Django process. We need the data laid out for us in a known spot. So we had to modify the Python runtime so that the interpreter keeps this metadata around, specifically about the coroutine creator. This way we can associate a coroutine with a stack that created it instead of the event loop. Now, this isn't perfect. The creator of the coroutine isn't always who ends up awaiting on it, but it gives us good enough data to make sense of most code. We provide the metadata you'd expect as well, falling into a few different categories. Stacks are annotated with host metadata, like which data center they're in, and which tiers, or groups of hosts, the host belongs to. This allows engineers to debug regressions that are caused by things like someone doing an experiment on a group of hosts, or some operational event that's specific to a specific data center or geography. We also provide request metadata like feature flags, the endpoint being hit, and the request latency. This is something that the earlier instrumentation-based approach was kind of giving us for free, but again, we have to work pretty hard for it. Since we're in a standalone process, we have no idea which requests Django is handling when we're profiling it. We need Django to tell us. To do this, we added some statically defined trace points to our request context. Our request context it's a common library that we use to track request metadata across threads and state changes. So just like with perf events, BPF allows you to hook up a program to a trace point. So when PyPerf is profiling, we have Django give us the request metadata at the end of a request. This is associated with all stacks we saw during the processing of a request. When we're not profiling, this trace point is a no-op instruction and has very little computational cost.
What about other processes on the same machine? Shouldn't we be able to run PyPerf on those too?
Yeah, absolutely. So although PyPerf has some Django-specific functionality, it's perfectly capable of profiling arbitrary C and Python programs. And hosts that are doing Instagram Django work have a bunch of other programs running concurrently. Things like various daemons and system scripts that are part of all Instagram servers. They can have regressions too. And that can affect the performance of the main workload of these hosts, which is to serve web requests. PyPerf profiles other programs on the host as well when doing a run, and the result is better visibility into the whole system. And we have a combined data set that allows us to do apples-to-apples comparison between Django and other programs.
How often should PyPerf profile a process? We want high-quality data without actually affecting performance.
Yeah, that's a really important question. So at the end of the day, regardless of how optimized our profiler is, it still has a computational cost. The way PyPerf works is it wakes up every minute and does a dice roll to determine whether it should run. As Pranav mentioned, our goal is to choose a probability of profiling high enough so that we can detect small regressions with confidence, but not too high so that we spend more CPU time profiling than necessary. There are a few concepts that can help us understand when to choose the right run probability. All the hosts that are doing Instagram web work have the same code and roughly equal workloads. They're part of the same service. And we care about monitoring the performance of the service as a whole, not any specific host. But since profiling is a per-host decision because we want to avoid coordination, we need to choose a per-host probability. We need a certain number of samples from the service as a whole to catch regressions of a certain size. So we tune how often each host profiles based on the size of the service and the size of the regression we're interested in catching. The size of the regression we're interested in catching, we basically consider a constant for this. Sometimes it goes down, but it will never go up. The per-host run, or the size of the service, however, changes frequently. So we update the run probability automatically and regularly to account for changes in the size of the service. When the service grows, we profile each host less frequently. When the service shrinks, we profile each host more frequently. But either way, we still get statistically significant data, while minimizing our impact on the production workload. So we wrote this fancy new profiler, but what we really care about is what effect it had on our data. As a reminder, here's the time series graph that we were looking at earlier. It's still pretty spiky and noisy. This is a problem for us because those regression detection algorithms we use, they notify engineers about regressions. So when an engineer sees a false positive, they might spend a few hours digging into a regression that isn't there, and they might get frustrated about that. Even worse than getting frustrated, if this happens too many times, the engineer might stop caring about this alerts. And that's not a situation we want to be in for efficiency alerts. Everyone has probably dealt with noisy, spurious alerts. Eventually, you kind of just ignore them until the problem grows hairier and larger than it ever needed to. Here's the same time series as seen by PyPerf. It's a lot smoother and easier to understand. As a result, our regression detection system produces more meaningful alerts, and we can generate these time series for native code, which wasn't possible before.
So we've been using PyPerf for over a year now, and it has been a big step forward in our CPU data collection. We've been able to catch smaller regressions with higher precision and recall, and the visibility into C extension, other threads, other processes on the same system has been great. I would say that PyPerf has been a key factor in our ability to hold the line on infrastructure demand growth. Some problems remain, however. We had to apply an actual patch on CPython to get async frame tracing to work. This is obviously not desirable, and there are many corner cases where the async frame tracing does not work. Python really needs a more holistic solution to the async frame tracing problem, and we'd be happy to work with the open source community to make this happen. So we've just talked about how the evolution of CPU profiling tools has helped us solve some of Instagram's scaling problems. You might have some similar problems at your companies, so here are some learnings that you can generalize and take away. Moving hard code paths into C, C++ is a common practice in Python and probably other languages too. Make sure you wait till you have full visibility into the area you're pushing your code into before doing it, because otherwise you could just be pushing regressions under a rug. While it's easy to build instrumentation profilers, it's probably worth it to invest in a solid sampling solution, especially if your products are growing really fast, because you've got to catch those small regressions to avoid your infrastructure demand growing. And if you have a fast-growing product, make sure that product teams are aware of the strain on infrastructure, but more importantly, empower them with the perf data that they need to fix regressions, plan and prioritize new features. Product teams are key partners to any successful efficiency program. Thank you for your attention, and we'd be happy to take some questions.
Thanks.
Thank you, Pranav and Dave. Let's start with Yuri, right in the middle.
Hi, thanks for the talk. Can you talk about how you dealt with the seasonality of the data after you smoothed the curve through PyPerf?
Sure. So there's two ways you can do this. The first is that you normalize the cost of a function with relative to everything else on it, or running on the server. So if you have the same seasonality across all your functions, you typically get a flat line instead of a curve. So when you look at normalized cost, you tend to remove some of the seasonality. Otherwise, you need to identify the individual frequency patterns in your data and try to eliminate them through Fourier transforms or something like that. Our algorithms have like seasonality detection and removal, so that when you actually compute the change point, it's accurate and you get the right delta.
Thanks, Pranav. Another question?
Hi. Since you used perf, it sounds like you used hardware performance counters.
Yeah.
So a modern Intel processor has like over 300 or more counters. Did you have any process to select a subset of those performance counters, or did you use all of them? And how did that sort of factor into your, the analysis of the charts that you came up with?
So on a continuous basis, we generally use things like CPU cycles, instructions, and last level cache misses. But PyPerf also allows you to do on-demand runs, where if you're a perf engineer, you can run PyPerf with a higher sampling frequency, for example, for any perf event you want. And generally, when we see people doing that a lot for perf events that we're not doing on a continuous basis, we reach out to them and talk to them about incorporating that into our continuous runs.
We have time for one more question. I'd like to ask it. Okay, we got one right here. So a mic will come. Yeah, it'll come. Mic will come your way. It's right behind you. Oh, okay. We have two more questions.
Okay, so Linux already have a perf program can do the profiling, and it can also do the Java profiling as well. What's the motivation, or what's the difference that you want to build something different, or try to expand that one?
So we use Python, right? And the perf profiler, for example, just gives you C stack traces. And that's typically not the metadata you need to debug regressions. You want to see Python functions. You want to see how Python calls into C++. You want to see these relationships. And unfortunately, the perf profiler can't do that for you.
Yeah, but the perf can be expanded to profile Java as well, right? So it is a multi-language profiler.
I think what you're asking is, why didn't we just extend perf instead of build a new thing? So in addition to doing the language profiling, we also need to do a bunch of Facebook-specific stuff. For example, we have a custom symbolication server that we need to call out to. So the work to extend perf to do everything we needed it to do, in addition to looking into the Python stacks, would have been equivalent to just building a new new service.
Thanks, Dave. And one more question here in the fourth row.
So I was just going to ask if you guys have looked into open sourcing this, or kind of already thought about integrating with the community outside. Sounds really cool. I'd like to have it. So.
Yeah, we're definitely looking into it. As I mentioned for the last question, there are some Facebook-specific parts that would be difficult to open source just because they're specific to our infra. But things like the BPF program and working with the open source community to get some of our coroutine creator stuff in so that we could open source like a good chunk of this is something we're definitely interested in doing.
Great. Thanks, Dave and Pranav. Thank you for the questions.